In the example for 4.3, we have a sliding mass on a tabletop. We'll call this M1. It has a mass of 3.2 kilograms. And it's attached to mass 2 hanging from a string over a pulley that has a mass of 1.5 kilograms. We want to determine the acceleration of each object. If you calculate the acceleration of any of these objects, it'll be the same. These two objects are connected by a string, and the string will cause the acceleration of the system to be uniform. The mass that is hanging and the block that is sliding will accelerate at the same rate. The only difference is now there is friction that is opposing the motion of this sliding box. So we're going to have to keep this in mind. You're going to follow the same steps that we've done to answer these questions in the past. So you're going to draw a free body diagram of mass 1 and a free body diagram of mass 2. Bless you.
Thank you.
So I want you to tell me what forces are acting on mass number 1. And now this question should be familiar to you because we've done one just like it. Feel free to look back at that note to recall how we answered this question. Paulina, what forces are going to be acting on this sliding block? So what's pulling it in the forward direction? Tension. And now what will be opposing this motion in the backward direction? Amazing. Let's look at mass number 2. What force will be pulling down on this object, Daniel?
Gravity.
And what force is going to be pulling up?
Tension.
Good. I've drawn tension in red for both of these free body diagrams. And the reason why is to stress the point that the tension acting on block number 1 is equal to the tension on block number 2. And if you remember, it's uniting these two equations based on tension that allows you to solve for the acceleration. Your next step is to list all the forces acting on each of these objects. So we're going to say the net force is equal to tension minus friction. And we forgot to make one assumption. Does anyone remember what assumption we forgot to make? Marla? Amazing. Let right and down be positive. If we do the same thing for this free body diagram, keeping in mind that down is positive, therefore up is negative, we end up with the net force is equal to gravity minus tension. What should the next step be?
Isolate FT.
Before we do that, let's replace net force with MA. So we're going to call this M1A is equal to tension minus force of friction. And here we'll say M2A equals, what can I replace gravity with?
Energy.
Good. So we'll say M2G minus tension. Now, as Rena said, we're going to rearrange these each for tension. So this guy here, tension is equal to M1A plus the force of friction. And this guy here, we're going to say tension I'm going to bring this tension over the equal sign, and I'm going to bring the M1A on the other side. So we get tension is equal to M2G minus M2A. Good. Since the tension calculated in this first equation is equal to the tension calculated in the second equation, we can say the first equation is equal to the second equation, just like we did in the previous example. So we have M1A plus force of friction is equal to M2G minus M2A. Now the whole point of this is to solve for acceleration. If we're going to solve for acceleration, let's make sure that we bring all of the accelerations together on one side and bring everything else on the other side. So we're going to bring this over the equal sign and get rid of friction. So we end up with M1A plus M2A equals M2G minus force of friction. Can anyone remember what the next step is? Factor out an A, so we have A is equal to M1 plus M2 is equal to, rather, M2G minus force of friction. So we're going to isolate A by dividing both sides by M1 plus M2. The acceleration is equal to M2G minus the force of friction over M1 plus M2. Now, my friends, you need to remember, force of friction. How do we calculate it? Force of friction is equal to the coefficient of kinetic friction times the normal force. So it's equal to coefficient of kinetic friction times mg. Since this object is resting on a level surface, we know that the normal force is equal to mg. So in place of the force of friction, we're going to say acceleration is equal to m2g minus the coefficient of kinetic friction times m1 times g divided by m1 plus m2. So this is very similar to what we did in question 1b on page 137, where we have gravity causing the object to accelerate and friction slowing it down, dividing it by the total masses. The only difference is now we actually have to calculate the magnitude of friction given the coefficient and the mass of the object. So let's sub and solve this, being extra careful as to what numbers you're putting in for M1 and M2. So you're going to have (1.5 kilograms times 9.8 newtons per kilogram minus 0.30 times 3.2 kilograms times 9.8 newtons per kilogram divided by 1.5 plus 3.2 kilograms. Punch it into your calculator and tell me what you get for the acceleration of this system. Take your time, do it carefully. You should end up with 1.1 meters per second squared. Write if you're referring to the block, or down if you're referring to the mass. Part B, they want us to determine the tension in the rope. We actually have two equations for tension. We can use this one, which corresponds to the free body diagram from the sliding mass, or this one, which corresponds to the free body diagram for the hanging mass. Either one you use will give you the exact same value. Let's choose this one because it reinforces our calculation of friction, and we'll be able to do that again for the second time, so we get extra practice. Tension is equal to M1A plus the force of friction. The force of friction from yesterday's note can be calculated using the coefficient times the normal force. What do I put in for the normal force? What do I put in for the normal force? mg. So this is m1a plus uk times m1g. Sub and solve, and you have the magnitude of tension. So 3.2 kilograms. We've determined the acceleration to be 1.1. Instead of meters per second squared, for this I'm putting in newtons per kilogram. Plus the coefficient from the question is 0.30. The mass is 3.2. And g is 9.8 newtons per kilogram. Punch this in and tell me what you get for the tension. So again, this tension is pulling to the right if it is referring to the block, or it's pulling up if referring to the hanging mass. In part C, they ask how far will the object move in 1.2 seconds if the initial velocity is 1.3 meters per second to the right. We've determined that this whole system is accelerating at a rate of 1.1 meters per second squared to the right. And we want to find how far the objects will move in 1.2 seconds. So in this question, we're using the acceleration that we've determined by analyzing this question through Newton's 3 laws. And we take that acceleration and link it back into kinematics. The equation that we use is delta D equals V1 delta T plus 1/2 A delta T squared. So we have an initial velocity of 1.3 meters per second to the right, which I'm going to leave as positive, times 1.2 seconds, plus 1/2 1.1 meters per second squared to the right, so I'll leave it positive as well, times 1.2 seconds, square that. Punch this in and tell me what displacement we calculate. So if you punch this into your calculator, you should get 2.4 meters to the right.